Hello, we're ready for our first talk of the afternoon. Scala 2.12 takes advantage of Java 8 and its new features. This brings opportunity but also complexity. Lukas will talk us through some of the challenges involved in creating Scala 2.12 and give you a good understanding of what has changed under the hood. Lukas's talk title is Tales from Compiling to the JVM.
All right, thanks for the introduction. Hello everyone, so my name is Lukas, I'm working at Lightband. I'm an engineer on the compiler team for about 3 years, I guess, by now. And yeah, I think you already heard the overview of the talk, so very quickly, what changed in 2.12 in terms of bytecode? So the two main things, if you want, is, well, the main theme is that we are taking advantage of the new features in Java 8. And the two main themes within that is the new encoding for lambdas. So we align with what Java does in terms of compiling lambdas. And the second one is compiling traits. We can make use of default methods within interfaces. Another part of the bytecode story in 2.12 is the new bytecode optimizer. But I'm not going to talk about this today.
All right, so here's the overview for the talk. It's really these two topics. Invoke Dynamic to compile lambdas. So we'll have a look at Invoke Dynamic under the hoods. How does it work? And then we'll dive into some of the specific challenges that we had adopting these new features for Scala. It's going to be a little bit technical. And the second part is about default methods to compile traits. So there's a few difficulties around supercalls to trait parent methods and how to translate those supercalls with Invoke Special, and also some considerations for performance of the compiled code. Maybe let me say, if you have questions during the talk, it's fine with me. You can interrupt me, no problem. All right, so Invoke Dynamic. Let me try to put it on 2 slides and hope you get the sense of how that things works if you're not already familiar with it. So an Invoke Dynamic is a new bytecode instruction, and first of all, there's 2 methods involved when you have an Invoke Dynamic instruction. The first method is called the bootstrap method, and it's executed exactly once, namely the first time that the JVM executes that instruction. And the bootstrap method is an ordinary Java method in a class file, and it gets a number of arguments. We'll see a bit more in detail later. But all these arguments, they are not consumed from the call stack of the current running program, but these arguments are kind of made up from the description within the bytecode. And so the goal of the bootstrap method is to basically provide a link to the actual method that will be executed when the invoke is run. So the linking of this Invoke Dynamic instruction happens at runtime, so it's dynamic in that sense, and it can be user-defined. You can do a lot of things with that. I'm not going into other use cases. We'll stay within how to use that thing for lambdas. And then, so the second method that is involved in Invoke Dynamic is the target method, and that's the actual method that will be executed. So this method consumes arguments from the stack and produces a result that will be put on the stack. And every time you visit in subsequent executions, the Invoke Dynamic is visited, that target method is executed. So how does it look in bytecode? This is not this is a very simplified representation. It's not even Java P output. So let's say you have an Invoke Dynamic instruction, so a bytecode. And the first thing, like every invoke instruction on the JVM level, has a name of the method that's being invoked. and the type, so the argument types and the result type. And this type here, it defines what happens in terms of the call stack. So it defines how many arguments the method will consume. I'm not talking about bootstrap, but the second part, when everything is bootstrapped afterwards. So these are the arguments that will be consumed from the stack, and this result is the type that will end up on the stack. And then in the bytecode description, there's a few additional things in there. So the first and most important one is a method handle, which is a reference. It's just like a reflection reference to a method. So it's a method handle to the bootstrap method. And this is the method that will be executed on the first run. And then there are additional arguments that can be encoded into the Invoke Dynamic instruction. And those will be passed as arguments to the bootstrap method. So, and this is customizable. So if you write your own bootstrap method, you can put your own stuff into these arguments. So how does a bootstrap method look? This is just, this is not even a correct, but a very simplified example. So you can define your own. It takes a number of predefined arguments. So amongst those are the name that is specified here and the types. So these ones you get as predefined arguments. You always get those in a bootstrap method. And then you can define custom arguments that your bootstrap method wants to take in order to do whatever it needs to do. And the result is always a call site. So a call site is a very simple wrapper around another method handle, which is called a target. And that target method is the thing that's going to be executed on subsequent runs of the Invoke Dynamic, also on the first run. So on the first run, we run the bootstrap, returns a call site, and then on every run, we execute this method to which the target handle points to. And I hinted at this thing here. In principle, the target method can be something final, a val, or it can be something variable, a var. So in the case of in the Lambda, or for translating lambdas, it will be always the same target method, we will see. But in theory, the system supports a variable target method. So you can change after the fact. The program can change the call site and change the method that will be invoked. Okay, so in the Lambda, this is a very simple Lambda up here. And I kind of assume you know what happens in Scala 2.11, so can very quickly repeat. We create a new class file with an apply method that so a single method that takes a string as argument, and this is the body. So there we generate a new class file. In 2.12, instead of generating a class file with this body, we generate a new method that implements the body of the Lambda. And then here's all the things that we need to pass to Invoke Dynamic in order to create the Lambda object. All right, so let's go through. Invoke Dynamic, the instruction apply is the name of the Lambda. All right, so maybe let's step one step back. What we want to create, right, is an instance of function 1 in this case, right? So function 1 is called the SAM trait here. So the SAM stands for single abstract method. So what this Invoke Dynamic thing can do is create an instance of a trait that has one abstract method, right? And this is the method that we want to implement in the end. All right. So these are all the things that are encoded in the bytecode and passed to the bootstrap method. So the first is the name of the abstract method that we need to implement. Here are the types of the abstract method that we need to implement. I'm wondering now if... Oh no, that's correct. Okay. And then, so here is the reference to the bootstrap method. And this Lambda meta factory .alt meta factory is a built-in thing in the Java 7, Java 8, Java 8 library. So we didn't write our own bootstrap method in order to use Invoke Dynamic for Lambdas, but we use the same that Java uses. And other things that are passed as arguments to this bootstrap method is the type of the the type of the single abstract method within the interface. So this is the interface, this is the name apply, and this is the type that we need to implement, that a Lambda meta factory needs to implement. And we are passing a reference. Again, it's a method handle, so a reflection reference to this method that implements the body. So with this information, Lambda meta factory can create a new class file, load it into the system, and then it can also create an instance. And that's exactly what Lambda meta factory does. So it dynamically synthesizes a new class file that implements the specified interface. And the returned call site, so that's the option, the object that points to this method that will be called by the Invoke Dynamic. So what the Invoke Dynamic call needs to do at the very end is create the Lambda, right? So an object. So the call site will basically be a reference to the constructor. And there's an optimization that is built in. So if a Lambda doesn't capture any values, then it will we can always reuse the same object, because every Lambda will have exactly the same behavior. So there's a built-in optimization in Lambda meta factory. If there's no captured values, you will always get the same Lambda instance. That's an improvement over Scala 2.11, where we don't do this kind of hosting. So we get that for free. Okay, now to the hard part. So that was the easy part. Everything worked out, right? So the first problem, or one of the first problems we hit, was boxing. So Lambda meta factory, it has built-in support for boxing adaptations. So here we have a user-defined SAM type, right? It has a single abstract method. And we use a Lambda, so this syntax here, to create an instance of T. And we want then, instead of generating a class file, we want to use Lambda meta factory to spin up like an instance of T and create that thing here. So the desugaring that the Scala compiler performs for the body is this method here, which takes an int as argument. And if you look at trait T, like the apply method is generic, and the argument type T will be erased to object. So there's a mismatch here, right? The function, the body method takes an int, but the apply method needs an object. And this kind of adaptations is supported, so we can just do it, and Lambda meta factory figure it out. But unfortunately, boxing and unboxing in Java and in Scala are not exactly the same, and the corner case here is null. So if you unbox a null in Scala, you get 0. If you unbox a null in Java, you get a null pointer exception. So here's the same example as before. If you pass, we create the T instance using the Lambda, and if you pass a null to this Lambda, we need to do a little bit of casting, but it's possible and it should work as it used to work in Scala 2.11, right? Then this thing is supposed to print null, supposed to print x colon 0 and not produce a null pointer exception. And if you just use Lambda meta factory without any additional considerations, it wouldn't work. We would get an NP. And therefore, we need to handle this case in the Scala compiler. And the way we do it is to synthesize an additional method that will take care of boxing the argument. And then we use this thing as the body method. So we pass this thing to the Lambda meta factory as the body, and then boxing will be handled correctly. Another example of the same problem is Scala value classes, which erase to primitives, but Lambda meta factory, of course, doesn't know how to convert between value classes and primitive types. All right, second problem, specialization. So this slide is not yet about lambdas, but just a very small example how specialization is translated on the bytecode level, or on the desugaring level, let's say. So here we have a class A that specializes the T on int, and we have otherwise the same as before, right? The single method apply. And we have a subclass that instantiates T to int. So here the apply method takes an int and just returns the argument. The desugaring looks like this. The interface, or the trait, let's say, but the interface class file will have an abstract method apply, which has the erase signature abstract, and it has this specialized method that takes an int and forwards via boxing to the abstract apply method. And then the subclass C, so everything of all of this is generated by the Scala compiler. The subclass C will have actually a override. Sorry, it will override the specialized method, because in the class C we know that the argument here is like it's always an int, right? So it will override the specialized method, and then it overrides also the forward. No, it implements the abstract method by forwarding to the unboxed version. So the problem here with using Lambda meta factory for this SAM trait A is that the abstract method is the generic one, right? So if we just create a lambda here for a t, then this is the method that the Lambda meta factory will implement. And the Lambda meta factory doesn't know anything about our specialization, and that means every call to this function here will incur boxing, which is of course a problem. Yeah, I should add that all the function 1 and function 2 classes in the stand library, they are specialized, and it would be a real pity to give that up for 2.12. Of course, we cannot afford to do that. So what we do two, let's say, smallish hacks, but they don't work. They work for 2.12. So for function n, we basically handwrite the specialized version instead of letting the Scala compiler generate them. And we make sure that the abstract method in those specialized function types, they are the specialized apply methods. So the Lambda meta factory implemented the right thing. So they are just handwritten classes, Java classes. And for user-defined SAM types, we basically don't use LMF, but we fall back to the 2.11 scheme of translating lambdas. We spin up an anonymous class at compile time, and we don't use Lambda meta factory. The real fix to this problem obviously would be to switch specialization to leave the other method abstract in the bytecode, but we didn't get around to do that. Good. Yeah. Okay, I'll just continue. So next problem. We're not done with Lambda meta factory, unfortunately. So one consequence of this new encoding is that we don't generate the anonymous class anymore at compile time, and that means flattening local things out can change the behavior. So here we have a local class C defined within the body of a lambda. In 2.11, this would desugar to a new anonymous function class, right? And the apply method. So all this code is just moved into the apply method. So the class C basically ends up as a nested class of the anonymous function. And since it's a nested class, it will get an outer pointer. So it will have a reference to the lambda instance. And because by default in 2.11, all the anonymous function classes that the compiler generates, they are serializable, this thing here will work. Well, assuming C is serializable, right? So this thing will work because the outer pointer of C points to the function which is also serializable. And with the new encoding in 2.12, where we have a method that is hosted in the class where we write the lambda, so it's hosted in A now. This class, the outer pointer of this class C now points to the A instance. And if A is not serializable, then this whole thing will crash. And apart from that, I think it's also a bad idea to serialize this A instance unnecessarily if it's not actually needed, right? So in order to fix this problem, we could fortunately piggyback on an existing mechanism within the Scala compiler. And let me explain this first. So final nested classes, they have a little secret that you might not be aware of. So small example, we have an outer class A, an inner class, a nested class B, and a final inner class C. And you might wonder, why are the two different? So what is difference between those two is that the class C does not get an outer pointer. So you can see that through reflection. We just load the class and look at all the fields. So the B1 has an outer pointer, C doesn't. And one way to exploit this in pattern matches. So assume here we have two instances of A, two distinct instances of A1 and A2. So they are not the same object. And if we create a new C, a new A1.C, we can match it on A2.C. And because the C instance doesn't have an outer pointer, this pattern match cannot verify whether the two things have the same outer. And so it will say, okay, in this case, well, if these things were B's, then you would get a match error. Okay, so the secret here is that basically final nested classes, they don't get an outer pointer if they don't use it. I mean, if you would use some stuff from A here, you would get it, of course. And so that's exactly the mechanism that we use now in order to get rid of the outer pointer within the local class. So if we have, oh, okay, let me go back to the example. Yeah, if you have the local class within the Lambda here, what we do is some analysis to see whether there are any subclasses, and if not, we basically mark this class here as final, and then the outer pointer will be automatically removed. Yeah. From here. Here. It's okay because, well, you could argue it's just as specified. That's the way things are implemented. But it's just that the C instance doesn't have. There's no way to compare the two A's in this case. So we have an object of type C here, right? And we just, the only thing we can compare in this object is its type, but we cannot check what is his outer because we don't have, there's no reference to the outer. And yeah. Okay, a very, very similar thing happens to local methods within a Lambda. So again, in 2.11, this local method is lifted into the anonymous function class. In 2.12, it's lifted into A. And so if you want to call this local method, you need an instance of A because it's a normal member method, a virtual method. And there's a new analysis implemented in 2.12 that will figure out if local is actually not using this. And if that's the case, then the local method is emitted in A, but as static. And that means we don't, like then in that case, the Lambda doesn't need to capture the A instance. All right. Yet another problem of a similar kind. So lazy vals. So a lazy val is guaranteed to be initialized exactly once. So this expression here, the one, well, this one doesn't have a side effect, but assume there's an expression with a side effect, we guarantee that lazy val is initialized only once under concurrent access. And we do that by synchronization. And if we just do the simple translation that we always had, what you end up is something like this. So you get an accessor for the lazy val x, and the value, so the int value that is finally stored and returned is an intref. The reason for that is, it's a bit technical, but basically, so x is not a field in the class A, right? X is created within the Lambda, and then it's captured by this other method, so we need to box it into an object that we can pass around. And the important thing here is that we flatten out these methods into A, and then we synchronize on this. And that's a real problem. If you have many local lazy vals within various expressions within A, then all of those, they synchronize on the A instance, and then you end up with deadlocks, right? And for fixing this problem, we got inspired by Dodi. So Dodi had this already fixed, and we just basically took the same approach. And the idea here is, the observation is that the lazy val is boxed anyway. A local lazy val is always boxed, and since there's a one-to-one correspondence between the lazy val and this box, we can just synchronize on that box instead of the enclosing object, and then we don't get these deadlocks. And for performance, we can kind of hope that the JVM's escape analysis would be good enough to hopefully get rid of this lazy int, which is a simple wrapper around an int. Okay, that was it for Invoke Dynamic. So as you see, plenty of difficulties. Usually start out with a simple implementation. You think, okay, that should handle most of the cases. It can be an effort, but usually it's more predictable. But then you end up with plenty of other stuff, and it takes a lot of time. And so that should give you a sense of this. Second part is about default methods. So yeah, default methods in Java 8, it looks like it's a very good match. It could be simple, let's say. So you have a trait with a method, they compile that to an interface. Default method, if a class extends t, then it will just inherit the method. Not much needs to be done, right? And that's true for the simple case. Some challenges mostly around, well, the main challenge is basically about these supercalls. So if there are cases when the semantics of Java and Scala don't match, and we need to implement a forwarder to pick the right method. See an example, but there's a number of difficulties around implementing correct supercalls. So as a reminder, here's what happens in 2.11. A trait t with a concrete method f, it gets desugared into an interface without body, obviously, and a separate class file with a static method that implements the body. And if a class extends t, then we need to provide this forwarder, right? There's no other way in 2.11. So for every method that you inherit from a trait, you get an actual implementation in the subclass that forwards to the static implementation method. Now in 2.12, there's if this is a default method with an implementation, then we can just scratch the forwarder, right? Everything will work. But there are still cases where we do need forwarders in 2.12. It's arguably corner cases, but of course we cannot just change the semantics. So here you have a class A with a concrete method f. You have a trait t that extends A, so it can override the method f. And then you have a subclass of t. So now if, where are we going? Yeah, so in bytecode, the interface t and the class A, they are unrelated because the superclass of an interface, it has to be object. You cannot change it in bytecode. So the fact that t extends A, it disappears in the bytecode. So what do we do for class C? Because c.f, it needs to invoke this method here, right? So what we do is adding a forwarder that makes sure method f, it invokes t.f and not a.f. And the way this call here is implemented in bytecode is Invoke Special. Okay, another case where we need static forwarders in bytecode in Scala 2.12 is JUnit method. So this kind of a special support that we built into the compiler after a few discussions. But the problem is that if you have like a test method in a trait and then a subclass that extends the trait, and JUnit 4 does everything through reflection, and it doesn't support default methods. And if class C doesn't have a method f, or a method run me here, test method, it will not find it. So we basically have a flag at the compiler level. By default, its value is JUnit. That means the forwarders in class C, the forwarder to run me will be automatically added, and JUnit 4 will be happy. Okay. So, okay, we had default methods implemented, and we're slowly wrapping up for RC1, and at some point decided to take another look at how fast is the compiler, how are things going, and realized there was a kind of a severe performance regression between, I think it was M3 and M4. And so the compiler got like 15% slower, and we started searching, and it turns out that we could nail it down to a specific commit, and it was the commit that stopped emitting these forwarder methods. So when we stopped implementing every trait method using a forwarder, the performance of the Scala compiler itself dropped by around 15%. Now, I think we are not fully decided yet on what will happen in 2.12.0 on this issue. So we have RC1 being released right now. In the next 1-2 days, it will be announced. And in RC1, This mix in forwarders flags is set to JUnit, as I said before. So there are no forwarders generated in general. And this means that the bytecode produced by RC1 could be potentially slower in every project out there. And we are very keen to hear your feedback if you have any numbers, not only on the compile time, not only on the performance of the compiler, but also of the performance of your code if you're using lots of traits. And if you have extra time, it would be super useful to compare if your code will run faster if you set this flag to true. Okay. Good. So we're going to talk a little bit more about super calls. So if you want to call a specific methods from one of your parent interfaces, how do you translate that to the bytecode? And let me first give a quick overview of Invoke Special. So Invoke Special is used for 3 cases in bytecode. It's used for invoking private methods, for constructors, and for super calls. And one thing we didn't realize until recently is, or we were not very aware of, let's say, that Invoke, I guess some people were. Anyway, Invoke Special is doing dynamic method lookup. So you cannot just say invoke dynamic t.f and it will invoke the method f defined in t, but in certain cases it will actually do a dynamic lookup. And the example here, so this is a like simplified version of the spec. So if you have a class C that extends B, so B is a superclass, and then you have a invoke special a.f, where, so if A, that thing here, is a class, and actually a superclass, like transitively, then the method lookup, it doesn't start at A, but it starts at B. That's specified. And if A is not a superclass or A is a trait, then method lookups will start at A. Right. And there's a bug in 2.11 and probably many versions before, where you can exploit the fact that we had a misinterpretation of the spec in this case. Again, it's a little bit intrigued, and it follows this pattern that there's a trait extending a class, which is a little bit weird and sometimes causes issues. So base class is A with F, then you have a subclass B that overrides F, and then you have a trait that extends A, right? And the class, so the class C has superclass B, so B.F is this guy here, but it also it mixes in T. And then we manually write a method that says super T.F. And according to the Scala specification, that thing should resolve to the method f defined in A. But the problem is we cannot even do that in bytecode, because if we write super A.f, the lookup will start at B and we get the wrong method. So in 2.11 you get the wrong answer in this case. In 2.12 you get a new error message saying that you cannot emit this super call. Okay, another small thing we didn't know so well and which is still causing a few questions about Invoke Special. So if you have an instruction invoke special t.f, then t needs to be a direct interface of the current class. So this is an example. Let's say we have a trait t, a subtrait u that extends t, and then c extends u. So this invocation here, if we translate it as invoke special t.f, then that's not legal because C doesn't directly extend T. And we tried various solutions to this, and the current one that we have in RC1 is that for every method that you define in a trait, we add an additional static forwarder. Okay, so you get the default method f, and you get an additional static forwarder that invokes this thing, and then we can use the static forwarder for the super call as we like. Okay, so that's mostly it for these corner cases. Maybe a small slide to wrap up. So all these changes, one of the very nice impacts that it has on the resulting jar files is that we can save quite some space. I cannot tell you exactly which feature was added when in this timeline. I don't remember the details, but basically, the main reasons that the jar files are getting smaller in 2.12 is the lack of anonymous function classes, and the lack of trait implementation classes. And you should. So the thing is that it's not only about these few bytecodes that implement the methods. That's actually the small part of these megabytes, but the main part of all these additional megabytes that you had in 2.11.8 goes into the constant pool, which has names to all the interfaces, to all the to all the method names, to all the types. And if we can have the trait implementation classes within the interface class file, basically you can use the same existing entries in the constant pool, and adding the code adds a very little bit only to the class file, but the class file itself, having a new class file, is always a lot of overhead. Okay, since I have a little bit of time left, I have one last completely unrelated example, but it's kind of amusing to see that sometimes things can go unnoticed for a very long time. So this is all the Scala code you need in this case, and it turns out the bytecode you produce for this object O, you can even scratch the parents, right? So the bytecode you produce for this has always been not according to the JVM spec. And the reason we didn't figure out is because the JVM was too lax about checking this, and they actually tightened this up in Java 9. And the existing bytecode that we used to produce would be invalid. It will throw a verifier, I think, in JVM 9. It was found by Dottie. That's why you have this dot here. So it's clearly written in the JVM spec that a static final field, you can only assign it within the class initializer, and it's not allowed to assign this field within the instance initializer. And we've been doing this for forever. I couldn't find any older version than 2.5, but I'm sure it's older than that. And since, yeah, okay, Scala 1.4, so. Yep. So the question is, how do you fix it? Well, it seems like you could just, so the class initializer creates a new instance, and we are storing the field within the initializer. It seems like you can just move this field store into the class initializer, right? But the problem is that it doesn't happen at the end of initialization, but somewhere in the middle, namely after the supercalls. So here we have a bit more complicated example. So object O, which does something in the constructor, and it defines a method, okay? And this something, it could be something else, it doesn't matter. But basically this expression here accesses the object and one of its methods, right? And in 2.11 this works because the module field is already assigned once the body of the constructor of the module is executed. So you can call a method, and this lookup of o.module and then .f will succeed. So if this is the current bytecode again. If we just move the module initialization into the class initializer, then it doesn't work because we end up calling this thing here, which actually doesn't correspond, sorry. So we end up calling this thing here before setting the module, and it will throw a null pointer exception. So what we did for 2.12 was just scratching the final from this field. And we'll see whether we stay with that solution or not. But finality of fields is anyway a little bit of a, how would you say, like a floating thing. It's not that clear. You can change a final field through affection, and so the JVM needs to make assumptions about final fields as well. They cannot just assume complete final and it never changes. So we don't expect that this has a big impact on performance, but we'll see. We'll see. We are in RC now. All right. That's it for my talk. Thanks for listening, and questions are very welcome. Yeah. Yes. So it's also specified that at the end of the class initializer, there's a there's a save point, or no, I don't know. Forget the terminology. But yes, we did think about it, and we could convince ourselves that it's supposed to be correct. Yes. Yes. Yeah. Yeah. Yeah, that's also a good question. Yeah, I think you're right. In case of multi-threaded access, maybe you would observe a null on the module in this case. Yeah, it's possible. Yeah. Oh, right. The JVM can also reorder things within a thread. That's true. Yeah. Yeah. So maybe it's a very bad idea anyway to support this. Yeah. Thanks. Yep. Right. Yeah. So right now, to be honest, we are not in the best position when it comes to infrastructure for performance testing, and so we do keep an eye on it, and it's a little bit of a mix, some tools, some manual stuff, and yeah, we constantly compare releases against each other, but it's really one of the things where we are lacking a little bit right now, and it will be one of the main focuses once 2.12 is out. Maybe now that we see a few issues coming up about performance, and maybe we'll have to invest some time even before 2.12.0. And yeah, unrelated to these specific problems that we observe now, it was on the roadmap, and it will be one of the things that we'll invest in to have better infrastructure. And yeah. All right, thanks everyone. Have a nice afternoon.